I'm Whitney. Welcome to Wyzant's Getting Ready for Precalculus. Thank you for joining me today. Today we'll cover functions and graphs. If you have any questions, please feel free to drop them in the Q&A and I'll try to help you with the answers. If it's something that I can answer right away, I will do that. And then if not, we can answer it at the end. We should also have time at the end for a little bit of miscellaneous Q&A as well. Let's get started. Okay, so today I really want to focus on getting comfortable with parent graphs and being able to recognize them and use them. So the main graphs that I think that you should know going into pre-calculus, you should be familiar with most, if not all of these, are on the board. So the linear one, you'll probably feel very comfortable with that one. That's y equals x. We also want to talk about their domain, their ranges, their in behavior, so what it's going to as it goes to positive infinity or what it's going to as x goes to negative infinity. So for the linear graph, y equals x, as it goes to negative infinity, we're going to hit every single x. And as it goes to positive infinity, we're going to hit every single x as well. So with that in mind, the domain, which is like what values x can be, is going to be negative infinity to infinity. Or you can also say all real numbers. We have parentheses on either side because you can't actually hit infinity, right? Anytime you get to infinity, there's infinity plus 1 waiting around the corner. For the range, that's the y values. So what y can be. In this function, you're able to get all the way up to infinity if you go this way, or all the way down to negative infinity if you go that way for the y values. Okay, for quadratics, or sometimes you'll learn them as parabolas, same thing, are y equals x squared. They can have modifications. It could be like x squared plus 2x plus 4, or it could be x minus 3 squared plus 2. But those are going to have a domain. You can plug in any single x. So its domain is all real numbers, just like the linear one was. The difference is the range. The range is only going to go from 0 to infinity here because you can't have negative values unless you were to do some kind of like shifting of the graph. So if you had a negative x squared graph, you would have from negative infinity up to 0. And if you see that bracket right there, that bracket represents that it can actually be 0. So you're allowed to actually hit y equals 0 on this one. Whereas you still can't hit infinity. The in behavior for the parent function, if you think about like what value y is going to as x goes to negative infinity, like following along this line, it's going to positive infinity. And then as x goes to positive infinity this way, y also goes to infinity. One second. Okay. Cubic functions, those are like x to the 3. So same kind of thing as linear. The domain and range can be anything because you're going to hit all those x values, you're going to hit all the y values. The domain, we see the negative infinity to infinity, and the range we see the same thing. In behavior, as x goes to positive infinity, we see y's going up to positive infinity as well. And as x goes to negative infinity this way, we see it going to negative infinity. Let's look at the square root function next. The square root function, sometimes you'll see it using exponents too. So square roots we can write as x to the 1/2. That number on bottom always represents like what power of root it is. So if you look over at the cube root real quick, the 3 would be outside the house, but the exponent would be 1/3, and like a fourth root would be 1/4, and so on. In a square root, you can't have negative x's. So this is the first time we've seen the domain restricted so far. The domain is only going to go from 0 to infinity. It's okay to have a 0 there. You just can't have like a -1 inside of a square root. If you've learned about imaginary numbers, that's why. The range can go from 0 all the way up to infinity though. So we're actually allowed to hit 0. And then like all the other ones, you can't actually hit infinity. Cubic roots, it's okay to have negatives inside because Like imagine if you had the cube root of -8. Cube roots are things where you're trying to multiply something by itself 3 times in order to get what's inside. Kind of like when you're doing a square root, you're multiplying it by twice to get what's inside. So if you were to take -2 times -2 times -2, -2 times -2 is 4, times another -2 gets us to -8. So it's okay to have negatives there, whereas there's no number that you can multiply by itself and get out with a negative. Because if you multiply 2 positives together, you'd get a positive, or 2 negatives together, you'd get a positive as well. Okay, exponentials and logs you may feel a little bit less comfortable with, but they're very important functions to know. So this exponential function, there's a couple characteristics that we want to note on it. The first one is that the x-intercept, or the y-intercept happens at 1. So that means if you plug in x is 0 to this function, anything to the 0th exponent is 1. So that's why we're crossing the y-axis there. We also see a horizontal asymptote right here. So what that means is the y value gets really close to 0, but it never actually touches 0, kind of like what we were talking about with infinity before. As far as in behavior goes, like I was just saying with the asymptote thing, so the limit as x goes to -infinity this way, or the y value is going to be going to 0. And then on the other side, as we go to positive infinity for x's, our y value is going to shoot up to infinity. This is going to be much faster than like a quadratic or a cubic would be, because every single time you move up in x's, you're multiplying by a. So like a squared is a times a versus, or if you're doing a cubed for an x is 3, it'd be a times a times a. So that's going to expand very quickly, and we're going to see a sharp increase up this way. For the domain and range, we're going to see -infinity to infinity, because you're allowed to plug in any kind of exponent there, and you're not going to run into any issues. But for the range, we only have 0, but with the parentheses, because we can't touch it, all the way to infinity. Okay, so a logarithmic function, or a log, is kind of the same thing, or same relationship to exponentials as squares and square roots are. So the quadratic to the square root, they're inverse functions. The exponential to the logarithmic's inverse function too. So what that means is if you imagine the y equals x line, it just gets reflected across it. So what we'll see happen is where we had a y-intercept of 1 here, we're going to have an x-intercept of 1 here. So that means if you plug in 1 to a log, you're going to get 0. We're going to see a vertical asymptote this time that goes to at 0. So that means x gets really, really close to 0, but it never actually touches. And in this way, even though it doesn't seem like it, this is getting closer and closer to infinity. It looks like we may have a horizontal asymptote there, but that's not the case. It's just going very slowly, even more slowly than a square root or a cube root would go. Your domain for this one, you can't actually plug a 0 into a log because of that asymptote there. So it's going to be 0 to infinity. And then your range is also going to be -infinity to infinity. For in behavior, you don't really have an in behavior on the left side because you're not going to -infinity for x's, but you will have in behavior on the right side because you will be going, you can plug in very big x's here. So when you plug in a very big x, you would get infinity. So your range goes all the way up to infinity too. Let's see. Okay, so that's kind of all the different types of functions I wanted to dive into. There's a couple I want to spend a little bit more time on. Some of these may seem pretty basic, but it's a really important tool going into pre-calculus, and it's definitely something that you want to be able to do quickly. So looking at our linear function, there's 3 different ways that you'll see it written. This first one is called point slope form. Sometimes they call it gradient intercept form. This next one is your standard form, It's not a very useful form. Anytime I see this one, I would recommend going ahead and getting y by itself. So you can move the ax over by subtracting. And then you could divide by the b on both sides and simplify. What that's going to do is it's going to allow us to have the form up above, which is going to be way more useful. And then this one is point slope form. It's going to be very useful if you can remember it for getting the equation of a line if you have 2 points, or if you have the slope in one of the points. Okay, so let's look at this first form. So this m represents the slope, the b represents the y-intercept. So if you're looking at the graph and you see where it crosses the y-axis, that's your b. If you can identify 2 points, and they can be 2 points anywhere, they don't have to be super close together. As long as you can count how much it goes up and how much it goes over, you can get your rise over your run, which is your slope. Or if you'd rather just plug into the formula, that's fine too. Identify which one's x1 and y1, it doesn't matter which, as long as you're consistent. And just plug straight in and you should get a slope out of it. Okay, so for practice, let's try graphing y equals 2x plus 5. What do you think our first step should be? So I would identify what the b is and put that on the graph, because that's going to be super easy to do without doing anything else. So we can say go to 5 and put a dot there. At 5, we're going to want to do a slope of 2. So this isn't a fraction, so you don't see your rise over run. If you want to make it into a fraction, you can do 2 over 1. So we can go up 2 over 1, up 2 over 1, up 2 over 1, and just kind of make that line. It's okay also to go back or down and then back. It's the same thing, because it's doing like a negative and then a negative, which turns out to be a positive 2 over 1 as well. It's just kind of like imagining it this way instead. And then that's your equation for that line. Or that's your graph for that line based on this equation. The other thing that you want to be able to do with linear graphs is take 2 points and find the equation of the line. So you could find it in any of these 3 forms, but the y equals mx plus b is going to be the easier one. So let's try that out. So we want to identify what x1 and y1 are, and x2 and y2. So I'm just going to label these here. We have x1, y1, and we have x2, y2. So then we can say that our slope is going to be y2 minus y1 over x2 minus x1, and we can just grab those points that we labeled. So it's going to be 1 minus -3 over -1 minus -3. So these negative negatives become a plus sign, so we get 4 over 2, which is just equal to 2. So now we have our slope. We can plug that into y equals mx plus b, but we don't have our b yet, so we're still going to need to find that. 2x plus b. We know for sure that both of these points need to be satisfied by this equation because they're points on the line. So one thing that we could do is pick either point and plug into here. So we could say 1 equals 2, -1 plus b, and solve for b that way. So we get 1 equals -2 plus b, and then b is going to be equal to 3. Either point would get us the same exact answer. The other way is using that point slope form. It's basically the same thing. You would just want to start with your slope. So you'd say y minus, and then either point works here. So y1 would be -3 equals your slope, which is 2, and then x minus, we're using -3, so we want to use -3 for this one as well, because it has to be coming from the same point. Otherwise, it's not the same point on the line. And then we get 2x plus 3. Some classes are okay with you leaving it in this form. If you're taking AP Calculus this year, then they would be fine with it. But usually in pre-calc, they want you to go ahead and solve for y equals mx plus b. So we would distribute this out So we get 2x plus 6, y plus 3, subtract from both sides, and then you'll get the same answer that we got this other way, the y equals 2x plus 3. So our final answer for this one would be 2x plus 3, regardless of which way we did it. Okay, let's see. Let's look at quadratic functions. Parabolas are one of the graphs that I see people have the most trouble with, but it comes up all the time. It comes up on the SAT, it'll come back in pre-calculus, it'll come back in calculus. So it's really good to get a firm understanding of like how to graph it, how to figure out the equation, and how to use it to solve equations as well. Okay, so here are your three forms. I like to call, let's see, I would call this your vertex form, this your standard form, and this one I call my zero form because it allows us to see where the zeros are. For the vertex form, your vertex is the point that sometimes we call it a turning point. It's the point where your quadratic turns around. That coordinate point we're going to call HK. So on your parent function, HK is 0. So that's where, and then A is 1 on your parent graph, so we would just get x squared out of it. But any type of parabola will work with this equation. So HK is your vertex. And A has to do with your stretching. So for all three of these, your A should be the same in the form. If A is greater than 0, it means it opens upwards. And if A is less than 0, it means it opens downwards. Your standard form doesn't give you your vertex like your vertex form did. The only thing it's really going to give you is your y-intercept, and that's C. So C is the y-intercept. For the zero form, it gives you your zeros. So this one only has 1 0 at 0, but other ones where they're shifted, like the one that we're about to do, we'll see the x1 and y1 in it. So like here, your x1 would be -4 and your x2 would be 2, or you can flip them. It doesn't matter which order. So here we're going to say x1, x2 are zeros or roots. Okay, so let's try to write out what we know from this guy into the vertex or the zero form. So for the vertex form, we have our vertex, we have our HK here. So we can just plug that in. So we have y equals, and it's going to be ax minus h. So minus -1 is our h. So we want to be careful with the signs here because a lot of students will mix it up. But h is the full vertex. So if you always remember it's x minus, then you can just plug that in and then simplify later. Squared plus, and then our k is -3. So we have y equals a, x plus 1 squared minus 3. That's not really enough though. What we want to do from there is we want to figure out what our a is. The only way we can do that is using another point besides the vertex. So you could use -4, 0 or 2, 0 and solve for your a from there. So here we could say, let's use 2, 0. So our y is 0, a, and then 2 plus 1 is 3, squared minus 3. If we move that 3 to the other side, we get 3 squared is 9 times a. So a is going to be 3 over 9, or 1/3. So then we can go back to the original one and plug in our a, and we'll have the full equation. 1/3 x plus 1 squared minus 3. The other way to do this will get us the same exact answer. We would want to start with the zero form, because we know both of our zeros. So we can say y equals a, and then we can do x minus, and then our first zero that we're going to use is -4. And like I said earlier, it doesn't matter the order that we do this in. And then our second zero is going to be 2. So that's x minus 2. So we'll get y equals a, x plus 4, x minus 2. And for this one, you can't plug in -4, 0 or 2, 0 because we use those to get the equation. So what we'd have to use is use any other point. The only point we know is the vertex, so we'd use that one for y and x. So if we plugged in -3 equals a, and then x would be -1 plus 4, and then -1 minus 2. That'll get us the same exact thing as that orange equation we found earlier. Okay, let's move on to looking at a different type of these questions. Let's see. For this one, you have your y-intercept, and you also have 5, 6 as the vertex. And we know it opens downwards, so that means our a is going to be negative. We don't need to know that to find the equation, but it's really good to identify that as soon as you're looking at a quadratic. So for this one, we would plug in and we'd say y equals a, x minus 5 squared plus 6. And then we can go ahead and use that y-intercept. So that y-intercept has an x value of 0 and a y value of 2. So we would just plug that in and solve for a. Plus 6. Oh, I forgot to plug my 0 for there. So for that one, we could go ahead and get our a. Once we get our a, plug back in. The next one, 4, 10, those are our zeros, so we'd probably want to use the 0 form. So if we were doing that, we would say x, and then it's always x minus, and then our 0 is positive 4, so we'd put in a positive 4. And then this one is x minus positive 10. And then we could do the same thing using our y-intercept. We could use the point 0, 6 to plug in. 0 minus 4 minus 10. And we would get our answer. Okay, let's move on to function characteristics. So function characteristics are things like x-intercepts and y-intercepts, which we've been talking about. Horizontal asymptotes, so in behavior, which we talked about earlier and how important that is. Holes, which are these places in the graph where you don't actually have a point. It looks like you have a point all the way up to it, and then it just kind of like vanishes at that specific point and then starts back up again like it didn't happen. And vertical asymptotes are places where it shoots off, the y value shoots off to infinity or negative infinity. So if you look at this graph, we have a x-intercept here and here. We're going to have y-intercepts, just one. And pretty much always, unless you're dealing with something that's not technically a function, you're only going to have one y-intercept. Horizontal asymptotes are places where it goes off and the end behavior goes to a constant instead of going to infinity or negative infinity. So if you look at this graph, as we go to negative infinity this way, we get closer and closer to this line. So like, let's say that this line was 6, then we'd have a horizontal asymptote of y equals 6. We also see that happen as we go to positive infinity. It doesn't go to negative infinity or positive infinity for the y value. It just gets closer and closer to this horizontal asymptote. So if this was -5, we'd also say we had a horizontal asymptote of y equals -5. Holes, so those are places, like I said, it just vanishes at, and the reason why usually has to do with the denominator. Maybe there was one form of the function that had a 0 in the denominator, but it canceled out, so we can't really see it going to an infinity or negative infinity. We'll get into that a little bit later, but to identify it on a graph, you're going to see like an open circle at that point, and you know from looking at that it's going to get close to that, but not actually hit that number. So like here, if this had been 3, we would say there was a hole at x equals 3. And vertical asymptotes are places where they shoot to infinity or negative infinity, and it doesn't matter which. So this one, the y value shoots to infinity, or negative infinity, sorry, on both sides. That's a vertical asymptote. Up here, it shoots to positive infinity this way, and it shoots to negative infinity this way. That's still a vertical asymptote because it's still going off to infinity. Okay, so let's do some examples. For this, for the x-intercepts, we're going to set y equal to 0. Y-intercept x is 0. Horizontal asymptotes, we're gonna talk about a trick when we see the functions to see whether it goes to a number, it goes to infinity, or it goes to 0. Wholes, we're going to factor and cancel. Vertical asymptotes, we're going to set that denominator equal to 0. But after we've canceled out all the wholes. That's a lot of information right now, so we're going to break it down problem by problem. Okay, so let's look at this first problem. The first thing I like to do is go ahead and factor it because I'm going to need both forms, but it's good to already have the factored form ready. So for this top function, or top part, it looks like we have an x squared in both terms. So we're going to want to pull that out to the front. So once we pull out an x squared, if you think about this divided by x squared, we have a 3x left. Plus 1. If you're not super confident in it, you can always try to distribute back and make sure you get back to the same thing. On the bottom, it looks like we can pull out an x. So then we'd get left with x squared minus 4x plus 4. If you get to a point that you can factor it even more, you're going to want to do that. So here, that bottom one, x squared minus 4x, is going to factor into something that multiplies to 4 but adds to negative 4. So the only two things that really do that are negative 2 and 2, or negative 2 and negative 2. So we can rewrite it as 3x plus 1. And then we have x minus 2, x minus 2. So for x-intercepts, remember, that was where we set y to be equal to 0. It's always flipped. So if we want this to equal 0, anytime you have a fraction and you want to set it equal to 0, you're only really worried about setting the top equal to 0. It doesn't matter at all what the bottom is as long as it's not also 0. The reason why is 0 over 3 is going to be 0 just as much as 0 over 10 is going to be 0. So if we do that real quick, we're going to have x squared 3x plus 1 equals 0. This is going to equal 0 if this is 0, or this is going to equal 0 if this is 0, because any number times 0 is 0. So that tells us we have x-intercepts at x equals 0 and x equals 1/3. Sorry, negative 1/3. Because in order for this to be 0, we'd end up getting negative 1/3 plugged in, because that's going to turn that into a negative 1 plus 1 goes to 0. Or if you want, you can break it out to the side, set it equal to 0, subtract 1 from each side. And then 3x equals negative 1, divide by 3 on both sides. For y-intercepts, all you have to do is set x equal to 0, so you're just going to plug that straight in. So you're going to get 0 squared, 3 times 0 plus 1, over 0, 0 minus 2, 0 minus 2, and just see what that's going to go to. This one, we should have canceled out. There's an x on top and bottom. So right now we'd run into an issue because at 0 we're going to have a hole, but we're about to talk about that in a second. So for the holes, once we have that factored form, let me rewrite it real quick. If you have anything that can cancel, that's going to be what we consider a hole. So here we have x squared on top and an x on bottom. If we cancel those out, we're going to just get left with an x on top. But because we canceled it and it was on bottom, we're not going to actually be able to have a function defined at that point. So x equals 0 is a hole. So remember, that looks like an open circle on the graph, and you don't actually reach that point. So we don't technically have a y-intercept in this case. For horizontal asymptotes, you want to use the fully unfactored form, and you're looking at the powers of each one. So you're looking at the cubes because they're the biggest power on top and it's the biggest power on bottom. So if you look at this term and this term, the way I like to remember these is if it's bigger on bottom, the horizontal asymptote is 0, Bobo. If it's bigger on top, it's undefined, which means no horizontal asymptotes. This is y is 0. And then if it's the same level of coefficients, then it's going to go to the coefficients, whatever fraction those would be. So this one falls into the category of same because we have an x cubed on top and an x cubed on bottom. The numbers in the front don't matter when determining how big something is. So since it's the same, it's going to go to the coefficients. So we have a 3 here, a 1 here. So our horizontal asymptote in this case is just going to be y equals 3. For vertical asymptotes, we have to jump back in to looking at the factored form after we've canceled out the wholes. So what we want to do there is set the bottom equal to 0 or the denominator. Here, the only way the bottom is going to equal 0 after we've canceled out the wholes is if x is 2, because this could be 0 or this could be 0, but they're both x is 2. So here our vertical asymptote is only x equals 2. So at x equals 2, we'd see that vertical line, and it would shoot off to positive infinity or negative infinity at that point. All right, so that's all we have time to do today. Do you guys have any questions that you want me to talk about a little bit more? Either anything that I covered today or anything else that kind of comes from last year leading up to Precalculus? Feel free to shoot it in the Q&A below. Okay, so we got a request for logarithmic graphs. Let me switch to a clean whiteboard. Okay, so the biggest, most often logarithmic graphs that you're going to see is y equals ln of x. So let's sketch out what that looks like. So if you think about that parent graph we saw earlier, it's going to go off like this. It's really important to remember that it can't actually hit 0. So you can never plug in an x of 0 there because it's not in the domain. We talked about earlier how it hits at 1 here. So any logarithmic graph, if you plug in 1 to here, it's going to be 0. If you plug in whatever the base is, so the base of ln of e, you could rewrite it also. We never write it this way because we have a shorthand, but sometimes you'll see log base of x. Whatever that base is, so here it's e, we're going to get a value of 1 there. And the reason why is because it kind of cancels out with the e. So if you plugged in e to this, the log e and the e would cancel into a 1. As far as like comparing different graphs, if you think about like log base 2 of x, or you could have log base 3 of x, the easiest way I think is to think about like where they would be at 1. So like e is like 2.7 something. So 2 would happen here. So it's going to hit 1 a little bit faster. So it's going to go through 1, hit here. And then it's going to go to infinity this way. 3 would be on this side. At 3, it would hit 1. It's still going to go through 1, 0 here. So we can see it go this way. And then it's also going to have an asymptote there. You probably won't have, unless you're dealing with a full unit on logs, you probably won't have to graph anything other than ln of x. So just that red function we graphed originally. The biggest thing I would focus on logs, or if you've learned your log rules, those are really good to review. So just a quick review of those. We have any log, ln we're going to see the most often, but any log this works for. So if you have log of a, and they have to be the same base, plus log b of c, then you can multiply them inside. So they're going to end up with the same base, and then it's going to be a times c. If you have log of b of a minus log of b of c, you're going to have log of b a over c. And then the other really, really useful one that you're going to use all the time is log base of a to the c. Logs are really cool in that they allow us to bring that c down. So that's probably the most used trick of logs, is that you can bring that c down. Okay, so I definitely review those and all of your exponent rules as well. What other questions do you guys have? Okay, well, we're waiting on another question to come in. I'm just gonna go ahead and write out the exponential rules. So if you have something to an exponent, let's say x to the a, and you're multiplying it by x to the b, we could do x to the a plus b. So those are gonna add if there's an x separating them. If it's x to the a to the b, then that's gonna go to x to the a times b. Another really cool one is that if it's x to the negative a, all that means is it's 1 over x to the a. And we saw earlier that x to the 1 over a is the 8th root of x. So kind of putting those all together, it's really important to be able to use those. All right, so that's all we really have time for today. Let me know if you have any questions. We're gonna send the link to this video to your email, so watch out for that. All right, thanks for joining us. Have a great rest of your evening.